Well, thank you very much, Nick. As usual, it's great to be in Manchester. It's great to be here. It's great to be here virtually. I had a terrible time getting through the airport last time I was in Manchester for real. Jack will see that I'm using what he calls, I think it was Jack who calls this the non-threatening font, Comic Book Sans in light blue. I want to go complete opposite to the abstract. I'm not looking forward. I'm going to look back. I'm going to talk about computers that I've known, and I want to talk to people that are here that are listening that I don't know, and tell you about some of the things I've been involved with. Many of my friends are here. They've heard some of these stories, but welcome to the rest of you. Welcome to everybody else. I want to, here is my first ever PowerPoint table. I spent a lot of time creating this thing. There's a lot of information there about computers that I've been involved with. That isn't all of them, but it's most of them, and it's the important ones in the places I've been involved with. And I'd like to tell you a few stories about some of those computers. The first one is this one. This was the first computer I ever used. This is the Burroughs 205 Datatron. I actually used two of them. One was at Caltech, where I studied where I took the numerical analysis course from Todd, and he had us using this machine. And then in the summer, I went back to my hometown of Salt Lake City, and the University of Utah had the same machine. So I had a summer job there. A few weeks into my summer job, the woman who ran the computer center then quit, and I was acting director of the University of Utah Computer Center the summer of 1960, when I was just 21 years old. Anyway, this is the machine. Now, can you see my arrow on this? You see my mouse here?
Yes, we can.
So here's the console. Here's a simulator of the console. Somebody has built a simulator of this machine. And the flashing lights were popular in TV shows. This is somebody working on the back of the machine. These here are electric tubes, vacuum tubes. And this was one digit. There are 8 tubes here, and that comprised one. This is a decimal machine, base 10 machine, and you would store one digit here, and these little things are mounted up here. So right up there is the A register, the accumulator in the machine. Important thing here is this drum. This was the storage. Memory was important in these early machines, however we did memory. This was a rotating drum. Think of it as like the drum in your dryer in your house. It's about that size, and it's rotating about 3,000 RPM. It's about the speed of your automobile if you're at idle. We wrote in absolute numeric machine language and punched our programs on paper tape. Because of the way the drum was organized, this is a long story, but it was important to have loops that were 20 instructions or less, and then they could be executed fast, rapidly. I had a program that we did some accounting for a local lumber store, and I had a program that had exactly 20 instructions in, only it didn't have a way to get out. It didn't have an exit. So I said, we need a skip on minus instruction. So the guy who maintained the machine, the graduate student in the electrical engineering, disappeared behind the consoles with a soldering iron and a blueprint. And he says, the opcode will be 51. So we had the University of Utah had the only 205 in the world that had a skip on minus instruction. Here's a sample program out of the manual. The clear and add, shift right, add, store. We were programming at that level of that level. Here's a representative shot of an IBM 7090. There were 7090s, 7094, 7090s, 709, 7090s, 7094s over the period. And we had these at Stanford and Jet Propulsion Laboratory, the big mainframes of the day. Here's a card reader. You'd put in stacks of IBM stacks of cards. These things are cards. You put in stacks, you program as a stack of those things, and you put it in this reader. That was the input. There's a printer back over here. So that's one of my programs. You zoom in on it, it says solve. This is actually going to become the Linpack benchmark and the backslash in MATLAB. Here is put together some of these slides about the PDP-1, the DEC PDP-1 at Stanford. This is a guy named Steve Russell working on the machine at the Computer Museum years later in a reconstruction. They got the machine running again. And that's because Russell had programmed the world's first video game, something called Space War. You would operate on it by operating these sense switches and manipulate rockets. There are two rockets here, and you manipulate them and fire missiles at the other rocket. It was important to be able to compute circles. He needed orbits. Russell needed orbits in the program. And so here is the pseudocode for the circle generator in Space War. Now, this doesn't actually generate circles, but it's close. You start out with certain initial values, you plot them, you load one of them in to the register, shift it right 3 and add the other one, store it back and store it back in the second one, change the sign of it, shift it right 3 again, add it, and store it back in the first one, and then repeat that thing. There's no trigonometry, there's no multiplication, it just adds and shifts. Why does that draw a circle? Here's, think of it as trying to solve the differential equation x dot equals minus x double dot equals minus x. So it's written as a 2x2 system in this way. This would be Euler's method for solving that. You start off with some initial conditions, and then you go, the new x is 1 plus h times the Jacobian times the old x. That's the explicit Euler. The implicit Euler, you solve a system of equations at each step. That's why it's implicit. So it's backslash in MATLAB. But here's what Russell's program is doing. And I'm calling it symplectic because this is an example of a symplectic algorithm. It's explicit in one component and implicit in the other. And that's crucial to its stability. Here is an animation showing the orbits, the solutions computed by, there we go. Okay, so the symplectic stays bounded. This isn't exactly a circle, but it's close. Euler spirals out. Its eigenvalues are outside the unit circle. Implicit Euler spirals in. Its eigenvalues are inside the unit circle. With the symplectic algorithm, the eigenvalues are exactly on the unit circle, so it's stable. So that was the symplectic algorithm from Space War. I'm not sure if that's what Russell knew it was symplectic. Here was another fun machine. This was the Tektronix 4081 at Argonne. Tektronix was manufactured oscilloscopes. Here they're going to make a computer. It's the only computer they ever made. They didn't actually make the computer. They had a 32-bit mini in here, but they had this display. That was about the time Armstrong was landing on the moon. So it was important to have a lunar lander simulator on your machine. One day, a guy named Ned Tannhauser showed up at Argonne. Tannhauser was the Tektronix engineer who had written the software operating system for this machine. He came to see what Argonne was doing with it. Jack knew he was coming, welcomed him, and we spent far into the night playing with the machine. Tannhauser showed up with a briefcase full of floppy disks with goodies on the machine. This is a cartoon that a friend of his made, and I think of this as Tannhauser underneath here. Jack somehow arranged to have pizza show up at Argonne. Jack knows a lot about pizzas since he was did that for how many years, Jack? 6 or 8? Well, anyway, so we had pizza, and Jack and I and Ned Tannhauser played with this machine. And Tannhauser ended up making a contribution to LINPACK. You see him acknowledged in LINPACK, and his contribution is on the table of contents of the LINPACK manual. So look up in the upper right-hand corner of the table of contents, and you will see Tannhauser's contribution to LINPACK. This is a stock photo off the internet of the VAX from Digital Equipment Corporation. The VAX is really just in these 3 cabinets. So there's not much to look at, except that when you open the cabinets, there would be a console connected somehow to what was in here. Here's a disk drive. And if you can just see the size of a platter that held the disks. So these disks were maybe more than 12 inches, maybe 15 inches across. And I don't know how much this disk drive held, but it was really just a few megabytes, maybe a gigabyte in this huge cabinet. But that was the VAX was a very important machine to us. So we had one at the University of New Mexico. Our computer science department had their own VAX, and that was breaking away from the central campus, and we got to use the machine just the things we wanted to do. And I saw them at Stanford and other places. That much of the development of the first MATLAB took place on VAX machines. Oh yeah. This is the Intel personal supercomputer. I left being a professor to go to Oregon to work on this machine. One of the world's first commercial parallel computers. Designed originally, the design at Caltech of something called the Cosmic Cube by Chuck Seitz, and Intel decided to commercialize it. Each of these, in this cabinet, there are 32 boards. Each board is like a PC of the day, with an 8286 and 8287 coprocessor, and I think 250K of memory, a quarter of a megabyte of memory was all that you had on each node. It was a hypercube connection, and we had homegrown primitive, this was before MPI, we had a homegrown primitive message passing to go between the machines. So between the nodes. So we learned something about parallel computing from this machine. It was not a commercial success. Its connection to the front end was not adequate, and they sold just a few machines. I left the Intel operation to go work on this machine. This is the Arden Titan. This was a try to make a graphic supercomputer, a cross between a Cray and a VAX and a Sun Workstation. This was meant to be used by one individual scientist, but it ended up being too expensive. It required 220 volts, and not a commercial success. But it did have MATLAB. This is the only machine in the world that ever came bundled with MATLAB. If you bought an Arden Titan, you got the MATLAB, MATLAB 3.5 on it. A graphic system called Dore. I learned much about computer graphics, about color maps, and so on using Dore on this machine. Then there's this machine. This was the first Sun Workstation. A lot of us had these machines, but this was now getting what started out to be in a whole room, an entire room full of electronics and machinery. In the first computer we saw, and again, a room full, even with the VAX, has now been reduced to this size, so it can go on your desk. And a couple of years later, that would become a chip, and we'd have the PC, and the big expensive monitor would eventually become the screens we have all now in the laptops we're using right now. So this was an important step in the miniaturization of the machine. And this machine ran Unix. So that was important to us. And again, a lot of the development of MATLAB, all these machines were, a lot of the development of the first MATLAB was done on this Sun machine. Okay, that's a look at some of the machines. I have a few pictures of Jack. You've already seen this one, the Lindback guys, the Lindback and the car, me and my sandals. Jack isn't in this picture, but he took this picture. This is Wilkinson telling me how to play cricket. The guys from NAG. Brian, I don't know where you were this day.
I was actually there. I was actually at the meeting, and Jim Wilkinson's here next to you.
Were you at the picnic?
He was. He was there. Yeah.
Yeah.
Okay. Anyway, here's Tom Hall, Hunstetter, Fosdick, Cowell. Here's Jeremy back here. Here's Brian and his kid here. Jack knows who these guys are. Anyway, that reminds me of what important.
What about this man here? This is Jim Wilkinson.
Well, yeah, I would say this is Wilkinson, was an authority on the theory of cricket, and he's giving me a lecture about how to play cricket. Here's a few pictures I have of Jack. Here's the Lindback guys 33 years later. Jack's lost the most hair, but I have the neatest shirt. Here's a picture taken. We had a birthday party for me at the new MathWorks headquarters. We just when I turned 60, so that was 20 years ago. And these three guys are together in that picture. You'll recognize those three. This is my daughter Cam in the background. Here's me and Jack together at a supercomputing meeting. I don't see him at SIAM meetings, but I see him at supercomputing meetings, and where he has a badge that shows how what how important he is in the organization's supercomputing meetings. And then this is also at supercomputing. 4 of us have dinner at supercomputing every year, and we're here with Sven. So here's John Gilbert and Rob Schreiber, as well as me and Jack, and then Ian was joining us. Not Ian, Sven was joining us, so we had a nice time at that supercomputing. Look forward to that dinner every year. And then as I was going through these pictures, I had one more. Oh no, there's 2 more. This is an important one. This is on the wall, on my wall in my office. It's a framed copy up on the wall behind me, and it's gotten faded. But I scanned it in. This is the best I can do with the color. These are 10 of my graduate students at the SIAM meeting at Stanford in 1982. Here's Jack down here, and across the front row are Chuck Crawford, Charlie Van Loan, Tim Davis, Jack, and Alan Klein. In the back row, Norm Schreier, Linda Kaufman, me, Jim. Oops. Okay, that's the last. I'll get me. Okay, where am I? Me, Jim Sanderson, and David Candler.
Advanced, yeah.
And Stan Eisenstadt.
Yeah. And Stan Eisenstadt. He's behind the. I don't see him on my screen because the picture showing all the participants is in front of that. But yeah, those were. I'm very proud of those guys, and glad to have this picture up there. Sanderson has had an interesting career in ecology, but I'm working with him now trying to revise some stuff he did about eigenvalues in his thesis. And then we have one more picture. This is Penny Anderson from MathWorks, and a couple of other people here, again, at that 60th birthday party. And people in Manchester. Here's Fran, and who's that on your lap? For which one? Who? Nick?
Probably Thomas. I'm not too sure, actually. No.
All right. Anyway, one of their kids.
I don't think it's one of ours.
Oh, it's not one of yours. Oh my goodness. This was 22 years ago. Well, I wonder who it is then.
Maybe Penny?
Penny doesn't have any kids. Oh, Penny does have kids. Maybe it's a Penny's kids. It must be Penny's kids. All right. So, yeah, okay. Well, I'm glad we solved that. So that's the computers that I have known. I just posted a blog that contains these slides and links to many other things in my blog where these things are discussed in more detail. You can get to it at that URL, or simply just Google Cleve blog, and that'll get you there as well. All right.
Right. Thank you very much, Cleve.